I'm excited about today's discussion because, as we travel the world and we interact with so many different magnetic suppliers and processing companies, equipment companies, characterization companies, we see all this, really interesting technology. Um, and yet, when we meet again with users of magnetic material, most of these technologies are really unknown to them. They're not in their toolbox.
Hmm.
And I think the one thing that we'd really like to be able to do with North and South is not just talk about polymagnet every single week, although, well, I'm sure we'll always sneak something interesting in about
Right.
polymagnet. But really, North and South should be a resource center for anybody doing magnetic design. And over the weeks and months, I hope that we're going to have a whole bunch of different interviews with different kinds of technologies, different magnetic materials, different processing, even different characterization tools, and the technology around that's just fascinating and developing. So hopefully,
Yes.
North and South can become your go-to corner for everything about magnets.
Right. Well, with that, I think we should like officially
Well,
start. We kind of slow roll in, but we should start.
I'll
So
turn it over to you and kick it off.
yes. Well, welcome to our monthly webinar series. As Tim very well articulated, our mission is to kind of bring all this knowledge and the key players and emerging opportunities into our magnetics world and share with everyone. We do record the sessions, so we post them so that people can partake of them and go back and re-listen, or if they happen to miss it live. So do welcome you to today's. We do it every month. Mark your calendar for next month, June 26th will be the next webinar topic, and we'll be announcing the specific topic in the next couple of days. So
I can't wait for that.
I know that is so exciting. These are very informal, so I encourage you to type into chat as you see fit if you'd like to comment or you have questions, and we'll kind of take those as we're going. So at this point, I'm going to turn it over to Tim
Great.
to go ahead and introduce today's guest.
Well, first of all, we've got to tell everybody how we even found this company. We were at an international magnetic show in Amsterdam. And I always like to kind of cruise the shows, spend a half a day just walking around and seeing what's around there. And a lot of times you'll just see a lot of magnet companies selling the same magnets that you've seen over and over again. But we ran across this company, MIMplus. It was a German company, technology company, that had just an incredibly intriguing manufacturing process for magnets. We're all kind of familiar with, basic sintering, creating blocks, machining magnets out of blocks, and all of that. But MIMplus has a unique capability to injection mold very precision, complex shape into net shapes. And it really unlocks kind of the creative genius of magnetic system designs, because no longer are we kind of stuck with almost kind of two-dimensional. I got a block. How can I extrude it? How can I cut it? It's got to be a flat cylinder. I can now start to think about creating these really interesting net shapes with their technology. And as you get more and more into it, you learn about their ability even to start to align crystalline structure and domains in the material and in different geometries and stuff. And I think our audience will be very intrigued by what they have. And I know since I met MIMplus, I've run into several companies that have had very unique challenges. And their kind of magnetic processing technologies, kind of uncovered some new ideas that they could use, and we'll cover some of those at the end of this. But
Yes.
I'm gonna turn this over to our guest.
Well, you should introduce.
I'm going to,
Okay.
and I'm just going to call him Dr. Florian, because anybody
No.
first of all, no, anybody that went through the entire PhD program deserves to be called doctor. So you know what? You're Dr. Florian, and at the end of this, I may ask you a little bit about my sore elbow and a few other things that I have. And,
Yeah, that's.
But Dr. Florian is
sufficient.
And he got his degree in one of the most prestigious universities in Germany at the Karlsruhe Institute of Technology. So he is going to come and talk to us about MIMplus, about injection molding, net shape manufacturing. I think you're going to find it fascinating, and when he gets to the end of that, we're going to have a little dialogue and talk about a few things. And hopefully, I'm going to ask him some questions that the doctor. Well, it may even stump the doctor.
Right.
We'll see.
Right.
That'll be the name of today's game. Stump the doctor. So, Florian, I'm going to turn it over to you. Welcome to North and South.
Thank you. And yeah, thank you, Melissa and Tim, and especially Tim for the very kind introduction. And thank you for giving us as a company, yeah, the possibility and the platform to be able to present to you our technology, which is metal injection molding of neodymium iron-boron magnets. I want to start my presentation with a short overview over our company and its history. Our parent company is called OBE Holding, and it's a family-owned company which has two subsidiaries, which is OBE. That is a company that is specialized in high precision products, especially hinges and small screws for the eyewear industry. And the other company is called MIMplus. That's the company I'm working for. And this company is specialized in the production of small complex parts or assemblies via metal injection molding. We have 4 production sites. Our main production site is in Germany, and we have one in Italy, in China, and very new, we have one production site in Vietnam. Where I'm sitting is our headquarter in Germany. I don't know how familiar you are with Germany, but it's located in the southwestern part of Germany, relatively close to the French border. It's a small town. It's called Isbringen, close to a city called Pforzheim. And maybe you have heard about the city Stuttgart, which is around 50 kilometers southeast from us. We have around 550 employees worldwide and a production floor of 25,000 square meters. I would like to give you a short overview over the history of MIMplus. We started nearly more than 120 years ago in the year 1904 as a tooling company for the jewelry industry, which was at that time very big here in Pforzheim. Then in the 30s, we transferred from solely tooling producing company to a company that was producing high precision products. For example, at that time, we produced small gear wheels for the watch industry that you can find in the watches. Then World War II hit. After World War II, there was a time of reconstruction. And in the 50s, we had what we call here in Germany, we refer to it as the economic miracle. And at that time, the company was really growing very fast, and we had a wide variety of different products. One of the most promising products at that time were hinges for the eyewear industry. So we were focusing more and more on that product. And in 1970, we invented and patented the spring hinge for the eyewear for glasses, which are used up until today. For example, I'm wearing glasses and I have this kind of hinge.
I think we all do.
Yeah, that could be. Yeah. In 1996, we introduced the metal injection molding process as one of the first companies here in Germany, or the reason for that was that the demands from our customers from the eyewear industry became more and more challenging. And with this technology, we were able to produce complex hinges that were not able to be produced before. Um, of
So,
course,
I'm going
yes,
to interrupt for a second, Florian. What's interesting, I think, about the history and the development of your company is the focus on really small, intricate, high
Mm.
precision componentry.
exactly.
Uh, and that's something that is not really associated generally with magnets. The smaller you get, the simpler they get, right?
Yes,
And we have all kinds of issues with fragility of magnets, the ability to machine really, small, precise magnets and things like that. So, marrying these two, kind of a company with a history of doing everything small and precise with with magnets is kind of unique, and I think that's why I'm so intrigued by what you've been able to do. Is it's really the history of your company, how you became, where you arrived in 2015 was a result of almost 100 years, right, of
definitely.
development.
Yeah. Yes,
So it's just kind of interesting historically how you got to where you are. I think it'd be really hard for another company to enter into this space directly because they don't have the background in this really
Mhm.
intricate, high tolerance, small component manufacturing.
yeah. Um, so with metal injection molding, of course, it's not only suited for hinges, but also for a wide variety of different parts. And that's why this sector was growing very fast in the following years. And then at one point, it was decided that uh, we make a spin-off of the MIM sector into a new company. And that's where MIMplus was born, which is now a subsidiary of the OBE holding. Um, yeah, and I think, Tim, you said it a little bit already, but what I want to point out with this slide is that in our more than 120 years of history, we were always a very innovative company who had to constantly reinvent itself in order to remain competitive on the market. And that's why we always are looking for new innovative products that we can introduce to the market. And that's basically what happened with the MIM magnets. Um, in 2015, we started with the magnet development, and the same applies to sinter-based additive manufacturing. Um, with this technology, we want to expand our existing capabilities to be able to also manufacture smaller quantities that are not profitable via metal injection molding. And in 2023, we then had our breakthrough um, of complex shaped magnets produced via metal injection molding. And we refer to it as our breakthrough because at that time we were able to produce for the first time MIM magnets that were comparable in its magnetic properties to a present sintered magnet.
Which is just incredible. Because
Yeah,
people have, injection molding magnets has been around for a while, but it's kind of like bonded magnets and flexible magnets and all these other kinds of magnetic materials where, yeah, you can make them, but they're not very good. They're weak. The coercivity is poor. Yep. And I
yeah.
think that's the major breakthrough of how do we do metal, how do we do injection molding of magnets, get complex shapes, and yet also end up with a really good magnet.
Yes, and it's not easy. So when you look at the history, it was 8 years of
Mm-hmm.
constant development. But I will come to that a little bit later, to some of the challenges. Um, some key facts about the company. We have a wide variety of different customers from different industry sectors, for example, medical, automotive, aerospace, mechanical engineering, luxury, consumer industry, just to name a few. Our core technologies are, of course, metal injection molding, And also to cover the smaller quantities, we have the sinter-based additive manufacturing since 2017. We have a very well-equipped lab for R&D, and we have in-house our own tool shop that produces our toolings for the MIM process.
Mm.
We have various post-processing possibilities in-house. For example, milling, surface treatments. We have an in-house galvanic that does the coatings of our magnets, for example. And what we cannot do in-house, therefore we have a network of leading suppliers. So to conclude, the company MIMplus Technologies specializes in materials technology and innovative manufacturing processes. And this is also the reason why, compared to the size of our company, we have a really big R&D department. We have a very close correlation to different universities here in Germany. So we more or less constantly have interns from this university and also offer to do bachelor or master thesis here in our house. The focus of our R&D department is basically on difficult to machine alloys, which could be functional materials like the neodymium iron boron magnets, which I'm talking about today, titanium and superalloys, two components MIM, and the additive manufacturing. And yeah, today I will focus on the permanent magnets produced via metal injection molding. So this gives you an overview over why we are doing that kind of magnets. Basically, what we want to do is we want to combine the advantages of the two conventional production methods, which is press and sintering and polymer bonded magnets. Press and sintered magnets, they are the strongest commercially, or neodymium iron boron press and sintered magnets are the commercially strongest available magnets at the moment on the market. But they can only be produced in relative simple shapes. On the other hand, we have the polymer bonded magnets. Here we have a very high level of design freedom, but when you compare the magnetic properties, they are significantly lower to a press and sintered magnet. And with
Dr.
our
Florian,
MIM,
you got to be careful when you say something like design freedom with a guy like me because I'll design anything. You know,
okay.
that was always my problem. Is once you told me I had design freedom, then we were in trouble.
Yeah, maybe we can talk about that a little bit later. Um, about the restraints in our process. But yeah, basically with
Yeah.
our MIM magnets, we combine the two advantages. So we have a high level of design freedom, not complete design freedom, and at the same time we have yeah, magnetic properties that are comparable to a press and sintered magnet. We can also realize complex magnetizations. And the big advantage is we don't need to do any post-processing when we do complex geometries. And at the moment, to our knowledge, MIMplus is globally the only capable supplier of MIM neodymium iron boron magnets at industrial stage. Here I have some examples of what could be possible to realize via the MIM process. But the problem is that we are working together with a wide variety of different customers, but we are not allowed, of course, to show their designs. So I have to alienate them a little bit.
Yeah,
Yeah, we're very familiar with that.
we
Yes. So on the one hand, MIM is very suited for very small parts. So we can produce tiny magnets. The minimum wall thickness that we realized was 0.4 millimeters. Then, of course, MIM is suited for complex shapes. Um, Here I have some examples. This is a holding magnet from the furniture industry. This is also a holding magnet from the electronic industry. And this is also a holding magnet with a cutout for a sensor and a cable routing. We are also able to produce multipole magnets, and we are producing magnets for e-motors. Um, and this is an example what would be possible to introduce to your magnet. This should be, or these holes are cooling channels. Then we have this dovetail, I think it's called like that in English, and a groove in order to be able to attach the magnet. Just to give the listener some ideas of what would be possible with the MIM process. Um, but we are not only capable to produce magnets from virgin material, but what we can also do is we can use end-of-life magnets and recycle them. We have the complete technical capability to do so in-house. And yeah, the plan is to establish a closed loop of magnet recycling in the following years, and therefore we are constantly involved in public funded projects and research.
Florian, I'm
Yes,
going to ask this question now because you talked about raw materials. Your supply chain of raw materials, I take it the majority of your raw materials, powders, all come from China because everybody's
yes.
do. Do you also have additional supply streams coming from other locations other than China?
Yeah, looking at what's happening in the world today, or at that time, that's a very important topic. And at the moment, we are trying to establish other supply chains apart from China. But to be honest, at the moment, we are at the very beginning.
Yeah.
Yeah,
And then the recycled material supply chain,
yeah,
those are magnets that somehow are recycled within the European community. And there's because the European community has kind of taken the lead worldwide in end of life, goods recycling, circular economy kind of work. So I take it there must be some market then for magnets in the European Union.
yeah, there is. But to be honest, with the recycling at the moment, we are at a prototype stage. So
Mm-hmm.
this is not. We need still some time to go into serious production with that.
Yeah, I've talked to several other companies. In fact, that's probably a good thing for a future North and South episode
Yeah,
is to talk. Maybe
recycling.
we'll get to, two or three companies that are all working on recycling together because it seems like everybody's about at the same stage. They've
Hmm.
done it. It's a lab thing. They've shown that you can do it, but nobody really seems to be at volume, yet.
Yeah. But maybe in the future we are forced to do so. We will see.
Yeah.
Exactly.
Well,
Again,
maybe in the future we'll do it just because there's end of life magnets and we might as well reuse them, right?
Yeah,
Keep them out
exactly.
of keep them out of landfills and
Okay. So this is an overview over our complete process chain. Um, what we did in the last years of the development of our process was we did optimization with nearly every process step in order to achieve a magnet grade that is comparable to a present-sintered magnet. What is also important to know is that from the powder production up until we have the sintered part, we need oxygen-free conditions. As neodymium has a really high affinity to oxygen, and every ppm of oxygen that we have in our final magnet will reduce the magnetic performance.
hmm.
So what we do, we start with our virgin material or our end-of-life magnets. The end-of-life magnets, we have a pre-processing step, which includes, for example, the removal of the coatings. With the virgin material, we can skip that step and go directly to powder production. The powder is then used to produce a feedstock that is flowable and can be used for the shaping in the injection molding machine. Then
Now,
comes, yes,
I'm going to interrupt again. This affinity for oxygen, that's not unique to your process, though, right?
yes,
Any process that involves powdered neodymium, right, it has this challenge with oxygen, right?
yes.
Um, Now, do you see everybody in the industry using inert gas in kind of an oxygen-free environment throughout processing, or do they manage it in some other manner?
Um, cannot talk so much about other industries, but I know that others, especially when you don't do near net shape, that they don't have a complete oxygen-free environment because then they
Mm-hmm.
cut out the magnet from the middle. But in our case, we definitely need that.
Yeah.
Um, okay, then we have the shaping of the magnet. And now comes the big difference to a polymer bonded magnet, because the polymer bonded magnet is done at that point. But our MIM magnet, for our MIM magnets, we have the next debinding step. That means that we remove nearly 100% of our binder. We do that in two steps. And after the binder is removed, we do the sintering. So then we can sinter the magnet to nearly full density and have our MIM magnet.
Right. And
After,
that's really the big difference between you and a bonded magnet, right? In a
exactly,
bonded magnet, you can do lots of interesting thing with bonded technologies, and they do. And as an industry, we use bonded technology because we can get these unusual shapes and characteristics. The challenge is that the binding material remains in the material lattice, right? So the concentration of the magnetic material it is interrupted by the fact that you have all this binding material
exactly,
in the end product. The secret sauce that you have is you use the binding material to generate a plastic fluid that can be molded, and then you remove the material so that we're left with just the neodymium boron, magnetic material.
exactly. And that's a very important point because we get that question asked a lot. What is the difference between a polymer bonded magnet and our magnet? And our magnets are really sintered magnets with comparable magnetic properties and also comparable physical properties than to a present sintered magnet. But I
Yeah,
will show
and
you some slides of that later. Yeah,
I think this is really challenging for a lot of magnetic designers, people that are um, familiar with what standard magnets, commodity magnets are available out there. I think they classify you instantly in that, oh, they're bonded magnets. We know all about those. They're not very strong, blah, 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 blah. But what you're really using is you're using the binding material to get to a near net shape, and then you remove the binding material to get back to a normal sintered magnet. So
exactly.
it's just a you know an interstitial step along the journey to getting to a near net shape kind of sintered magnet.
Exactly. So the polymer is only needed to get a flowable feedstock that can be used
Mm-hmm.
for the shaping process.
Right. I think that's the biggest challenge in communicating this to people. It's not a
Exactly.
bonded magnet. We don't have residual binding material, right? This is a sintered magnet. The fact that we get to near net shape during this process using some kind of plastic sizing bonding material, right, is almost irrelevant to the end product.
Exactly. Okay, now we have our sintered magnet. Then we can do in-house some post-processing like tumbling. We can also do the plating. We have different coatings that we can apply to the magnet in order to protect it from oxygen. And the last step then would be the magnetization.
I tell you, that then the last step in magnetization, this is what got me so interested when we first met in Amsterdam. is, two developments that we're working on from an R&D perspective, the micro head, right, which is a very, 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 very small area of magnetization.
Mm-hmm.
And then also the integration of our magnetization heads with kind of 6-axis robot capability. So you have the ability now to magnetize around very unusual, complex shapes.
Exactly.
Both of those to me are really interesting companion technologies to your injection molded net shape capabilities.
Now, so I want to go a little bit more into detail on the powder production and the feedstock production. Basically, the powder production is the same as for a press and sintered magnet. We are using our raw material or end-of-life magnets. We put them here. You see our raw material that is strip casting flakes. We put them into a reactor that is filled with hydrogen. The hydrogen diffuses into the material, which goes along with a volume expansion, and then the material falls apart, and you get a relatively coarse granular. And this material is then transferred to a jet mill, where the material is milled to a defined particle size distribution, and then we have our powder. The fun fact about the powder is that as soon as it comes into contact with oxygen, it ignites. So it's pyrophoric, which is really fascinating to see when you see it the first time, but of course it's unwanted. So we really need to make sure that we stay under oxygen-free conditions, especially here with the powder. The next step would be the feedstock production, and that's what's different compared to a press and sintered magnet. We take the powder, putting it in a special designed compounder, mix it with a polymer blend and other additives in order to get our feedstock. This feedstock can then be used for the shaping process. Therefore, we use conventional state-of-the-art injection molding machines. And with our in-house tooling shop, we manufacture specially designed toolings that have an internal magnetic field. The reason why we need that field is that neodymium iron-boron has a magnetocrystalline anisotropy. That means that it has a preferred magnetization direction along a specific crystal axis, which is the 100 direction. Then
I think that, that's
yes,
absolutely critical. Your ability to introduce these fields, especially in different areas of the net shape magnet, is critical so that you don't end up with just an isotropic, type
exactly,
of material. Because again, a lot of interesting things have been done with magnets, but they either end up with bonded magnets or they end up with isotropic, right? Which means you're not going to get really strong magnets. You've solved all of those problems where not only have you gotten rid of the binding material, but you've also been able to align the domains such that they optimize whatever the function is.
exactly. And that's also something we always have to explain to our customers, which is very important to understand, because the degree of alignment, like you said before, it's really critical with regards to the remanence. So we need to achieve a very high degree of alignment to achieve a high remanence in our magnets.
Yeah, I remember when we were in Amsterdam, I was talking about the ability to create kind of a monolithic Hallbach array.
Yes.
Right? Because you have the ability to align your domains differently, right, throughout the injection molded part. And then, of course, the question is, but how would you magnetize it, right?
Yeah.
And if those interstitial domains are aligned at 45 degrees rather than 90 degrees, then there's a chance that we actually could magnetize those, vertically and at 45 degrees, creating an effective monolithic Hallbach array, which is really, to my knowledge,
in one magnet.
and one, that's
Yeah.
a monolithic. It's a single piece. I don't think that's ever been done by anybody, and
Yeah.
it would really be an interesting a piece of R&D work to do, I think.
Yeah,
Mhm.
that will be my next slide. Um, but back to the alignment. Yeah, we did some experiment or investigations via EBSD scans and also via X-ray diffraction in order to see how does our alignment work. And from these experiments, you can extract a lot of parameters that describe your alignment in the magnet, and the result is that we are comparable to a present-centered magnet with regards to our alignment. And this is the complex magnetization that is also possible in our or during injection molding. So what we can do is we can influence the orientation of the magnetic field lines in our cavity. And for example, with that, we can produce multipole magnets, or we can manipulate the orientation so that we can either produce radial or diametrical magnetization. And what you said before, Tim, was with the Halbach arrays. So
Mm-hmm.
that would be also possible to introduce an alignment to get an Halbach array, a monolithic Halbach array. Um, then after the shaping, we have the debinding step. And it's really crucial to remove nearly 100% of our binder. And that's also a lot of development work we had to do in the past. This is some experiments I did a few years ago. We have here on the y-axis um, the remanence in blue and the coercivity in red as a function of the carbon content in our magnet. And what you basically see is that both magnetic properties decrease with increasing carbon content, but the coercivity between 580 to 660 ppm, it does a very sharp drop of coercivity. Our guess is that at that point, the hard magnetic Nd2 Fe14b phase is disintegrated by the carbon, resulting in a shift to other areas of the phase diagram, which could lead, for example, to iron phases that are not wanted in the magnet. And these contaminant phases then act as nucleation points for reverse domains. So it's really crucial to remove the entire binder from our magnets in order to get good magnetic properties.
And when did you achieve that roughly time wise? Like how many years ago did you finally figure out how to remove the binding material to a level that was sufficient so that you could compete directly with sintered magnets?
I would guess I was already at the company, and I would say roughly in 2022.
Mm-hmm. So, for our listeners, the key is, this is relatively new technology. So if you're sitting out there going, I haven't ever heard of this. Yeah, because these developments and these amazing technology breakthroughs that have been, achieved at MIMplus, they've, it's been a culmination of almost 100 years of science, art, practice, research, development, and technology. But it's all come to fruition here really in about the last 3 years.
Yeah. Um, then we have removed our binder, and then it's possible to sinter our part to full density or nearly full density. And yeah, this is basically the main challenge to remove the whole porosity from our magnets, because this is also a crucial influencing factor on our magnetic properties for
Mm-hmm.
especially the remanence. These are also some experiments I did a few years ago. This is the correlation between the remanence and the porosity. You see an almost linear correlation because the pores, they act as that space and do not contribute to the magnetic flux. And so it's really crucial to eliminate the pores to the best possible extent to obtain a high remanence. And
Well, and because you're injecting complex, three-dimensional shapes, there's a lot of science here of how you end up with your final net geometry. If you didn't care about tolerances, it would be one thing. You could smash and bake and do all kinds
yeah,
of stuff to eliminate this, but you're trying to hit an end tolerance on a three-dimensionally, designed and toleranced part. So the science of that is really also a special sauce of MIMplus.
yeah, and also now we are really able to achieve porosities down to 2%. And this is also comparable to a presence-centered magnet.
Mm-hmm.
Okay, now our magnet is sintered. We can do some post-processing and the magnetization, and now we have our MIM magnet. And now it's of course interesting, what are the properties? Um, Here I have a demagnetization curve of a MIM magnet. The blue line is at room temperature, and you see with the remanence, in this case, we are around, I think in this case, it's 1.36 Teslas and coercivity of nearly 1,800 kiloamperes per meter. Um, so this would be a kind of a grade of N45SH.
Mm-hmm.
And you see the demagnetization curves at elevated temperatures. We are also able to measure them. And when you take now the remanence, which is of course decreasing with increasing temperature, and also the coercivity is decreasing, and plot the relative remanence and the relative coercivity over the temperature, you also get a linear correlation. And from the slope of that line, we get the temperature coefficients for the remanence, which is minus 0.11% for each degree C or Kelvin. And for coercivity, it's usually higher, which is here 0.46% for each Kelvin. And these values are comparable to a presence-centered magnet. The
Yeah, I was
same,
wondering. It almost seemed to me like you might have a temperature advantage because you have this teeny bit of porosity that almost acts as insulating layers in the magnet, right? That would have been an interesting issue whether or not you could have gotten
yeah,
the
if we
machine
if we
prepared.
would be better, but
Yeah, yeah,
no,
very
unfortunately,
interesting.
we are not.
Well, you're the same. That's okay. It's
It's the
okay to be
same,
the same.
which is good. Also, the density, it always depends a little bit on the chemical composition of our raw material, but it's also comparable to a presence-centered magnet. And we also measured the specific electric resistance because that's always important for our customers that are using the magnets in e-drives. And also, this is comparable to a presence-centered magnet.
Mhm.
So, uh, those MIM magnets are really sintered magnets with equivalent physical properties to a presence-centered magnet. Um, then I have a slide over as an overview over the different magnet grades that we are at the moment able to achieve. The black data points are points for a sintered stage. Um, and they have different chemical compositions. So this high remanent magnet has no heavy rare earth elements in its raw material, and then with increasing heavy rare earth or yeah, with more heavy rare earth elements in it, then the remanence is decreasing and the coercivity is increasing. So we have a trade-off between remanence and coercivity.
Mhm.
Here we are in the area of an N48 grade. In the middle, it's around N45 H grade, and then the high coercivity magnet would be an N40 SH grade. We are also able to do grain boundary diffusion. With that, we can shift the data points more to the right to higher coercivities. And here we have something like N45 SH grade.
So the same tricks of the trade that everybody uses to improve coercivity and stuff like that
Exactly.
really are they're available to you as well.
Exactly. If when you have the MIM magnet, you can do the same things. For example, you can also do heat treatments and all the stuff that is done for a presence-centered magnet. And we are
Fascinating.
constantly improving our magnet grades. So our next goal, that's where we're working on at the moment, is to achieve an N48 SH grade.
But that's because you have an entire building of PhDs that all they do is want to create the
They're
next great
all,
thing.
yeah, that's true. So this is my summary. I would like to conclude my presentation that I hope it became clear that our MIM magnets that we produce here at MIMplus offer you the possibility to do unique magnet designs, tailored magnetizations, and at the same time with excellent magnetic properties. So as a customer from us, you have unprecedented possibilities, yeah, to be able to do with our magnets.
You know,
Yes,
you kind of I think you just blow everybody's mind. You know, the ability to think completely outside of the box of
exactly.
how small I can go, what kind of precise geometries I can take, what kind of net shapes I can be dealing with. Uh, it just it makes from a designer perspective, I think it just frees up the application completely. I know I ran into just a stupid simple application, you know, it none like the ones you've shown, but you know, it's straightforward. A lot of people use magnets in shear, and magnets, they're not very good in shear, and in this case they were in shear, and they were in shear on a mesh surface, so not a solid plane, but it was actually kind of a mesh. And the ability to create an interlocking texture on one side of the magnet that would actually interlock with the mesh, so that the magnet didn't have to carry all the shear, but you had a combination now of mechanical lock and
Hmm.
attraction, right? Uh, completely change, you know, completely changes what they can do, the amount of force, the amount of shear that they can hold, and dramatically reduce the size of the magnet, because all you're trying to do now as a magnet is keep the interlock in place, you know.
Yeah,
So, you know, just completely changes design, which is I just really interesting when you start thinking through the things that you can do. What's one of the most interesting applications that you can talk about without having, being locked up in an asylum someplace?
Yeah.
yeah, that's exactly the problem because we at the moment we really have, and that's a really cool thing. We are working together with a lot of innovative customers who now really understand the concept and the capabilities that MIM offers them. But it's hard to say something. But maybe just to keep it very general, what is really interesting or what I really like is one customer had the or came up with a very innovative design and a very innovative arrangement of the poles. And that makes it possible to use raw material with lower or with no heavy rare earth elements and to
Mm-hmm.
get to the same performance
Yep.
uh,
Yeah,
in
we've been
in the
working on a lot
application.
of those conversions as well.
Yes.
You know, you've got this kind of 6 to 1 to 10 to 1 ratio between ferrites and neodymium, depending on what
Yeah.
grades you're using, and and all that kind of stuff. But there's so many things you can do with geometry and magnetization, multi-pole designs, etc., that in many cases you really can substitute the two. And when you do, then you're out of the rare earth business. You're 70 to 80% less expensive. Overall in the magnet design, it's really remarkable what can be achieved. So before we leave, one thing I'd ask is, from a designer's perspective or engineering perspective, what design considerations or tolerance issues do I need to think about with respect to injection molded magnets? How small can I go? What kind of tolerances can I put on the part? What kind of feature sizes within the net shape would be too small, perhaps, to think about? Could you give us any general rules of thumb?
So general rules is, as a designer, you definitely have to consider the design guidelines of injection molding, or it would be beneficial to consider
Mm-hmm.
them. For example, avoid material accumulation so you don't get any, or you reduce the probability of getting shrinkage cavities, for example. Um, you should, if it's possible, avoid undercuts.
Mm-hmm.
Um, it's not necessary. We have some techniques so that you can also have undercuts, but it would be beneficial. Avoid sharp corners, all that stuff that corresponds also to injection molding. Regarding the tolerances, we always say the tolerances without any post-processing are around 1% of the nominal length. So that explains why small parts are very suited for MIM, because then the tolerances are smaller.
Incredibly tight. Yeah.
Yeah, exactly.
Well, fantastic. What an
I
incredible
know this is so educational, right? But you did a really good job of breaking it down for those of us who don't have that doctor in our title.
Well, I
It
hope we
really
really have
helped.
opened the eyes to magnetic designers that there's a new world out there for not only net shape manufacturing, high coercivity materials, not having to suffer all the drawbacks of bonded magnets, etc. You know, that if we really understand the entire network of companies that are out there doing these leading edge, technologies and capabilities in magnetics, we can design better systems. We can design
Yeah,
better parts. We can do things that we've never been able to do before, thanks to the people at companies like MIMplus.
great.
So, Dr. Florian, thank you so much for sharing your expertise and your knowledge of this really fascinating magnetic technology. And
Yeah,
I hope to run into more and more customers that I can send your way, and they can solve really unique problems. And hopefully, together, we'll build a better world.
yeah,
Yeah.
that
All
would be nice. And
right.
yeah, thank you as well for giving us the platform to be able to present our technology.
Very good.
Great. Well, thank you so much. Thank you so much to our Polymagnet fans who joined us and will be listening in the future. And join us for our next webinar on June 26th. So more info to come on that.
All
Thanks so
right.
much. Bye,
Bye bye,
everyone.
everybody.
Bye bye.